So we're kind of in this question, we're looking at a moving rod in a circuit. So in the figure we have a resistor. It has some resistance of 50 ohms. Then we have the length of the circuit, which is 12 centimeters. Then we also have the width, which is x. Actually, we don't have the width. The width is x, and we have a velocity though, and this rod is moving at this velocity, and it's moving in this direction as this vector shows. Now what's going to happen is the rod is moving this way, so you're going to have more area. The area is changing. That's something we've already noticed. The area is changing. That's awesome. And then it says to suppose that B is, the magnetic field is also changing. We're describing it as a function of time. The moment we're hearing the word change, this means derivative. So just keep that in mind. Rates of change is basically a derivative. So there are two things that are changing in this problem. First is the area, because as the rod moves in that sorry, give me a second. There we go. As the rod moves in that direction, we get more and more area, we get more and more width. The x value, this x variable is changing. So we're asked to find the induced electromotive force. Induced as in you're gonna be induced, and an induced EMF just means that you're going to use a magnetic field to cause a current to start flowing in something, and usually a something like an inductor, a metal, like an allow the flow of electrons, so hence allow current to flow through. So yeah, you're just creating a magnetic field, which we have done here, which is going to cause a flow of current. Now the way it looks like, assuming that you're watching this on your tablet, and your tablet is flat on the table in front of you, your thumb, your magnetic field, or your thumb is going to point into the table down towards the floor. As you curl your fingers, we're using the right hand rule here, your fingers are going to curl in the clockwise direction. So at least with the magnetic field that we are right now, like shining on this loop, on this rectangular loop, we're thinking that the current is going to flow clockwise. We can't assume what it's actually going to do, but we're thinking that it's going to flow clockwise. If I look at the magnetic field, the equation for it itself, it's changing, and I'm just going to see if it's increasing or decreasing. It seems like the magnetic field is decreasing actually over time. Yeah, it's decreasing over time. It's getting weaker. Because you're doing 10, a constant number, minus 5 times the time. So you could do 5 times 1 second, 5 times 20 seconds, and realize that at some point you're going to get negative values for the magnetic field. The magnetic field is decreasing. So, if it was just a magnetic field that was decreasing and not the area, then we would sort of want, the current would actually decide to, if the magnetic field was decreasing and only the magnetic field and nothing else, the area was the same and the angle was the same, then basically the current would try to actually strengthen the magnetic field. It would always, the current will actually oppose the change. So if the magnetic field is getting weaker, which it is in this case, it would try to make it stronger. So instead of making the current flow clockwise, the current would try to flow counterclockwise, and the current would basically create a magnetic field in the hold on. No, actually I'm wrong. It would be the opposite. The current would actually continue to flow along it would continue to flow clockwise. Since the magnetic field is getting weaker, it wants to try to flow clockwise to strengthen the magnetic field. So the magnetic field created by the current itself, the induced magnetic field, would also point with the original magnetic field, the external magnetic field, to try to strengthen the magnetic field. Because the thing is that what the current is really trying to do is it's trying to survive. If the magnetic field keeps decreasing, at some point it's going to hit zero. And then at that point, the current is going to die. The current's trying to live. So again, sort of coming back to this question itself, the area is changing too, not just the magnetic field. That's what we're trying to keep in mind. So we'll try to solve this problem. What I said previously was just something basic, the theory, kind of introducing you to the theory behind such problems. So I'll start with the equation of magnetic flux, which is what we're going to need, and then we're going to follow it up with this equation. These are usually two equations we use more often than not in this kind of in these types of questions. I'll start with the flux. The magnetic flux is equal to the area. What is the area? It's the length times the width. How do we know that? Because we're dealing with a rectangular loop here. The length is a fixed constant, which is 0.12 meters. That's awesome. But the width, the x, is changing. It's not the same. So I'll just write it as x for now. Multiplied by the magnetic field. The magnetic field is also changing. So it's 10 minus 5 over s, 5 per second times time. S just means seconds here. It's just a unit. I'll make this equation smaller. Times the cosine of the angle between them. Now, the way my teacher taught me the equation for magnetic flux is that the area vector has a normal vector. Well, we basically call the area vector and the normal vector the same thing. In my class, my teacher used the normal vector, but they're the same thing. The area vector always points perpendicular to the loop itself, perpendicular to the actual area. So in this case, like if your tablet is flat on the table in front of you, your loop is basically in the XY plane. It's sitting in the XY plane. In another way, you could say that your loop is the table. And so your normal vector is either going to be pointing with the magnetic field or opposite to it at 180 degrees. So in the positive k-hat direction or in the negative k-hat direction. You can choose whichever direction you want to point the area vector. This is another notation we use for the area vector, the normal vector, or you can also call it the normal vector. So what I'll do is I'll choose the same direction for the normal vector as the external magnetic field is. So I'll say negative k-hat. So now basically I want to find the angle, right? The entire reason I'm doing this is to find the angle between the area vector and the magnetic field vector of the external magnetic field. In this case, it's going to be 0 degrees because I've assumed the area vector points in the same direction as the external magnetic field. So it's going to be 0 degrees. When you take the cosine of 0, you get 1. So this entire thing is just 1. Now to continue with the magnetic flux, basically I know that the length is a constant, but my width is changing and my magnetic field is changing because of this function. So what I'll be doing is I'll take the derivative. To show that these things are changing, I can't find a fixed value for them. So basically, I'll use the constant rule to sort of like take this guy out. So it's just going to be 0.12 meters times the change in width over change in time times the derivative of this guy. I can simplify it much more. the derivative of 10, the derivative of a constant is always 0, so that's done for. And then the derivative of the following 5t would be the constant rule, so 5 goes out, and then you take the derivative of t, which is just 1. So that's what you get, 0 minus 5 times 1. And again, forget about the s. It just represents the units. It represents seconds in particular. Forget about the units for now. So what we're getting is 0.12 meters times the change in width over change in time times minus 5. Now here's the thing, I have made a bit of a mistake. Instead of writing the magnetic field like this, I'll write it like this. So basically when I'm trying to take the derivative, I know that this guy is changing and this guy is changing, and they're being multiplied with each other. So this was just a constant. I won't worry about the units. I'll get rid of them. And I took the derivative. So derivative of x, a variable that is changing, times the derivative of the magnetic field is also a variable that is changing. When both of these guys are changing, we're using product rule for derivatives. That's the first thing. So don't do that mistake that I did. I took the derivative without thinking about what was actually going on. The best way to solve this problem is actually to start off with just the variables. It's easier, and then plug in the numbers at the end. So I started off with the numbers, and that's why I got confused. So we know the width is changing because there's a velocity vector for the there is a velocity moving the rod away, increasing the area. Now when I take the derivative of this, I use product rule, so I'm getting 0.12, that's just a constant, it doesn't matter, dx over dt times b of t plus x times the change in b over change in t. Now x is the width. When I take its derivative, I could also think of x as the displacement, or the position. When I take the derivative of the position over the derivative of time, that represents the velocity, which we've been given here. So I do 0.12 meters, which is just a length, it's not changing, and that's 2 meters per second, the velocity. Basically what I'm trying to say is that the width is kind of like the position or the displacement, hence assuming that its derivative is the velocity, times b of t. Now in this case b of t is just this function, 10 minus 5 per second times time. Plus, now we're looking for the position. So we have to assume that x is 0.4 meters, so that's fine. And then we actually have to take the derivative of this guy. And when we do that, we get 0 minus 5 times 1. 0 minus 5 times 1, which is just minus 5. Now, it said to find the induced EMF, the current, and its direction at a time of 0.5 seconds. So the question's kind of acknowledging that, yeah, like the area is changing and the magnetic field is changing, and so that's why they've given us the value of time, a specific value for time. So we can actually solve for the change in the flux to eventually get the actual EMF. So the time is 0.5 seconds, and here we have the time, the t. So I'll substitute 0.5 seconds for the time. I'll use a smaller font so the seconds will cancel. So when I kind of simplify this further, I get 0.12 meters times 15 minus 2, which gives me 15 minus 2 is 13. So for the change in flux, I get 1.56. And the units, I believe, are Tesla meters squared. So we found the change in flux, but we actually have to find the EMF, which is going to be the following formula: minus n change in flux over change in time. Now in this scenario, we need to find n. N is just the number of loops, or the number of turns. In this case, we only have one turn, or one loop. So hence the number of turns is just 1. And we plug in the change in flux. And we get an electromotive force that is negative 1.56 volts. So a negative EMF just means that our current is actually flowing. So yeah, I get a negative electromotive force, which means that my current is not actually moving clockwise. My current is actually moving counterclockwise. So a negative EMF just means that your current is actually moving in the opposite direction than when you initially assumed. Basically, when I assumed that my area vector was pointed with the magnetic field vector, I basically assumed that it was trying to strengthen the magnetic field because the magnetic field is getting weaker. But that's not the case. It's not just the magnetic field that's changing, it's also the area. And because of that additional factor, the normal vector was actually pointing away. So the angle was 180 degrees between the magnetic field and the area vector. So because of that, my current is going counterclockwise. So current flows counterclockwise. And now I just need to find the current. I'm going to do some erasing. So here we are. That's our EMF. We just use Ohm's law at this point. That's the only thing left to find the current, and then we're pretty much done with this problem. So this problem was relatively straightforward. The reason I would consider this a harder problem is because two things are changing. In these kinds of problems, three things can change: the area, the magnetic field, or the angle between the area and magnetic field vectors. this is like a general mind map for these types of problems. And so in this problem, two of these three things were changing, the area and the magnetic field, and hence I had to use the product rule for the derivative. Usually in the simpler problems, only one of the three one of the three things are changing, either just the area or just the magnetic field or just the angle. So you could maybe see this problem in a test, just because of the fact that it's a bit harder. Now, going back to finding the current, we just use Ohm's law. V is equal to IR. We have a resistance already, that's the 50 ohm, and we rearrange for the current. The induced current is now V over R, which is negative 1.56 volts, divided by 50 ohms, which gives me a current of 0.0312 amperes, and it's negative. So again, the fact that the current was negative tells us that it wasn't actually flowing clockwise like I had assumed, assuming that the area vector was pointed with the magnetic field, the external magnetic field. So this negative sign means that it was actually flowing counterclockwise. The orange arrows show that. So that pretty much solves the problem. Now, just one other thing. I just want to explain this current thing a bit more. If your EMF and your current are negative, that means that your normal vector or your area vector is pointed in the wrong direction. It doesn't matter though, you don't have to erase all your work. Like your teacher will just see that, okay, you assume that it was in the other direction. It doesn't matter, they're not going to deduct marks for something like this. Again, it's sometimes in certain questions like these, like choosing your area vector either at 180 degrees or at 0 degrees is a choice that's like doesn't really matter, even if you get a negative answer or whatever. Basically, when I just assumed that the area vector was pointed with the external magnetic field, I assumed that the current was flowing clockwise. But it turned out that the current was actually flowing counterclockwise because of the negative sign. So that was my initial assumption, that it was flowing clockwise, but that was wrong. It was actually counterclockwise. That's all that you have to understand from this. And then sometimes you'll get the answer correct. It will be positive, and that means that you chose the right direction for the area vector. But you won't be losing marks. There's no like right or wrong direction for the area vector. That's just me trying to explain things so that hopefully you could understand these negative signs and why they pop up. Thank you, and have a good day.